Hey team, Chemistry Coach coming at you. We're going to be looking at some lab stuff you're going to be doing, although I could put this on an exam as well, but this is more fun to do in lab. Oversimplified view, we'll do a little more specific thing on the next board, but collecting a gas by displacement of a liquid, typically water, because water's pretty inexpensive in lab. So again, very, very common lab technique. Briefly talked about it when we talked about gas mixtures. Let's look at it more specifically and how we account for some issues that we run into in the laboratory. So if we want to capture, we run a reaction and generates a gas, and we want to capture that gas, measure its pressure, measure its volume, all that kind of stuff. Very commonly, what we'll do, we'll take a vat of, it could be any liquid, as long as the gas does not react with the liquid. If it reacts with the liquid, you get a problem. So if it reacts with water, you probably can't use water. So people in the past would use maybe mercury or something. That's a lot of fun. Don't do it though. Don't play with the mercury. So here we have, well, what we do is we take a tube, sometimes like a gas collecting burette, which has etchings on the side so you can read the volume directly on it. And you fill that tube up, and I'll try to do that. I don't know, I don't want to get water all over my laptop, but I'll see if I can do that quick demo in a second here. And what we do is we fill that collecting tube. Could be a test tube, it could be a collection a gas burette, whatever it is. Fill it up with that liquid. So if it's tap water, DI water, whatever, fill it up and invert it so that the water can't come out, and insert it into this vat of water. So it's complete, there's no air in there. There can't be any air to start with, right? It's completely filled with liquid. And then take a tube or something from wherever, so maybe you're running a reaction in a test tube or something where you can collect the gas and not lose it to the atmosphere, right? So that you're guiding that gas through this tube into the collecting device right here, right? And then what you'll do is you actually see bubbles of that gas going up. You'll see the bubbles coming up. And what happens when the gas comes up, it pushes liquid out. So it's displacing an equivalent volume. So the volume of gas generated is equal to the volume of the gas, of the water ejected from the particular collecting device there. So say this reaction's over and we see the water level drop in the collection, maybe the gas burette down to here, right? We have an issue, and I'm going to blow this up into a bigger scene on the next page here, the next board. Inside this test tube, you've got that gas, right? But it's not pure, because remember, we're displacing water. You see that liquid water there? At whatever temperature it is, temperature gives kinetic energy, right? Would you agree that the water molecules have a certain kinetic energy on the surface there? So they're going to evaporate off the surface. I'm going to talk about that in more detail on the next board. We're going to take this little thing and blow it up so we can have it over the entire board and really look at this. But you're going to have some water vapor that comes and peels off the surface of that liquid water. And now that water vapor is mixed in with your gas. So that gas is not pure. It's contaminated with water vapor. And you now have a mixture. Oh no. So if we measure the pressure of this, the total pressure, it's not the pressure of the gas. We have to correct for it by subtracting out the partial pressure of the water vapor, or we call the vapor pressure of water. So I'm going to get a table that shows you, and it's on my website for my class, that shows the vapor pressure of water at different temperatures, and we'll talk about that on the next board. So I'll get that, and then we'll see if I can do a little demo. Let me see if it works first, because if it doesn't work, I'm going to get water all over my laptop. Not good. All right, gang, I'm risking the livelihood of my laptop on this demo. So what I do is imagine this is your vat of water or whatever liquid, and here's my collection tube. So that's filled to the brim with water. I just have tap water. So you can just get some paper towels. It's a fun little trick. You can use like a stopper or something in lab. I just like to get a little piece of paper towel. Fun little trick you can do at home. Just put that piece of paper towel on the top. You ready? Please work. Oh, look at that. Oh my goodness. You see how no air got in there? So what I can do is I can now put that in here, shake off that paper towel, and now I've got an inverted tube with you see no air bubbles in there at all, right? This is fun if you take like a piece of calcium or something, put the calcium in there, and then you start to see the production of bubbles. you can invert this, put this over the calcium, and those are hydrogen gas bubbles. You can collect the hydrogen gas, and you can collect it by displacement of water, and you actually see the water level dropping as the gas comes up and displaces it. It's really fun. Then you can take that out, and hydrogen's flammable. You just put the test tube next to a Bunsen burner flame, and whoop, you get this little blast of flame coming out. So much fun! Yay! Yeah, for flammability. But same thing true, if I had done a bigger experiment, let's say I had generated a gas in some chemical reaction and I was able to create some tubing or whatever to come up under here, and the tubing went up inside that test tube, the bubbles of gas would come up, push out the liquid, and let's say at the end, it pushed out the liquid to, right about here. Boop! If I could match this up, right about there, right? Oh, I lifted it up above. See, the water came, so it looks like that now. Ha! I lifted it up above the water level and air got it. But say it looked like that when you're done. You'd have your collected gas in there, but you would also have some water vapor, because every liquid, the surface above that liquid, the molecules of the liquid water, if they get enough thermal energy or kinetic energy, they can peel off and go up, I'm free, up into the gas phase. And if it's in a sealed container, it's like, if it rains in California, there'll be puddles of water around. Very rare, once every 2 years or something. But the puddles don't last forever, and they certainly never boil. Can you imagine going by, hey, Dad, the puddle's boiling, isn't that bad? Yeah, that would be bad. So even without boiling, that puddle goes away, because each layer, surface layer of the water, peels off over time, and in time, it all vaporizes away, even though it never boiled, right? So at any temperature, water's going to peel away. Would you agree the higher the temperature, the more thermal energy or kinetic energy it has, and the more molecules pop off? So I kind of showed here, here's the liquid water. The purple is the gas collected, so maybe we're collecting oxygen or nitrogen or hydrogen or something. But the little blue ones are water, gas particles of water that peeled off. They got enough thermal energy to pop off into the gas phase and then go, whee! But in a sealed container, they're stuck. And some of them may go back and hit the liquid level and suck back into the liquid. But there will, at some temperature, you'll get an equilibrium where the number of water particles will be constant in there. And the pressure they exert is the partial pressure of that water in that mixture. We call that the vapor pressure, or VP of water. That's a contaminant we need to worry about in our lab, because if we're going to do the ideal gas equation, PV equals nRT, with the gas collected, we can't use the total pressure, can we? We need the pressure of just the purple gas. So what we're going to do is we're going to probably use a barometer or a manometer to measure the total gas pressure, and then look up on a table for the water vapor pressure at that temperature, and then just subtract it. Use Dalton's law of partial pressures. So as temperature increases, the vapor pressure increases. Hopefully that makes sense to you. And the identity of the gas matters as well. Identity of the liquid. Some liquids are more volatile, go to the gas phase more readily. That will be something we talk about in second semester general chemistry in a little more detail. But I will provide you in lab and on exams a vapor pressure table. So what I did is I just typed this up. Right? These are in millimeters mercury, or torr. So what you do is just look at the temperature. Right? So starting at 0, this goes from 0 all the way to 56.0 degrees Celsius. So as you move to higher temperatures, you can see the vapor pressure of water increases. See that? And we're typically at room temperature, somewhere in the 20 range around here, maybe 21. So say it was 20.5 degrees Celsius, that would be at 18.2 millimeters mercury partial pressure or vapor pressure of water. If we were up here at, say, 22.1 degrees Celsius, it would be a 20.1. The partial pressure would be 20.1. So you just read the table. These are up on the walls in my lab. But you can print that out and bring it with you to lab, and I'll provide that on exams. So you can look up the vapor pressure, just you measure the temperature. We're usually going to assume the temperature of the gas is the temperature of the water typically. And just look it up, find that, use a barometer or a manometer to measure the total pressure. You can get the pressure of your individual gas collected, right? So let's write that up here. So P total is the pressure of the gas plus the pressure of the water, right? Let's whatever gas that is. Let's say that was hydrogen gas. Right? Say it was we say we were collecting hydrogen gas, like with a piece of calcium in here. So inside this tube, you'd have some hydrogen, and you'd have some water vapor in there, a mixture of both. So if we want just the pressure of that gas, right? So the pressure of the hydrogen would be the total pressure minus the vapor pressure of the water. So in lab, this is always the first step we have to do. And once we've corrected that, then we can do gas law stoichiometry calculations. So again, this is from the table, and that's usually measured from a barometer. Possibly a manometer, just depends. It's pretty easy to do, actually, once you know how to do it experimentally. But I just wanted to introduce this concept of partial pressure to you. So let's do an actual example of what you might run into, a simplified version of what you might do in lab, where we're going to do a gas law stoichiometry problem. So maybe take a solid, decompose it, or do some kind of chemical reaction, maybe drop a metal in acid, generate some hydrogen gas, or I could take, say a metal oxide, decompose it to produce oxygen gas, or potassium chlorate, get oxygen gas, whatever it is. Take some kind of azide compound, try to get nitrogen gas from it. And let's say we produce that gas and then collect it by displacing water, measure the temperature. We can get all the parameters for PV equals nRT to get moles of that gas. We just have to correct the pressure. It's kind of a first step. And then we're just in a gas law stoichiometry problem. So let's have at it. You ready for something very similar to what you might do in a lab? Like very similar. We're just not going to do this reaction. But this is kind of a fun one. It's very similar to, again, how your, I think your bags, if you get an experiment, your airbag deploys. I don't know if it's sodium azide or some other form of azide, but typically you'll see that the N3 with a -1, that's a polyatomic ion called the azide ion. It's really cool. So if you have 2 moles of sodium azide in the solid phase, right, decompose it, you get 2 moles of liquid sodium and 3 moles of nitrogen gas, and that nitrogen gas goes, fills up the bag pretty readily. So let's say we were able to run that in lab. We set up a water displacement device, right, where we invert, put water in a collecting gas burette, invert it, maybe run this in a test tube, get some tubing over there to collect that gas by water displacement. And let's say we measure the temperature of the gas is 23.4 degrees Celsius, right? And we collect the nitrogen gas by displacing water. The volume read off the gas burette was 34.71 milliliters. That's how much, so the bubbles are coming in, the water's dropping, boop, we get 34.71 milliliters. And we doing a little thing on the experiment where we adjust our experiment so that the total pressure of our gas mixture, which is the nitrogen gas plus the water vapor, right, is equal to the surrounding atmospheric pressure. I'll show you how to do that in the laboratory. So let's say the barometer reads 762.7 millimeters mercury after, if there's any corrections for the measurement in the lab, that's already been taken care of here. So we're going to make the assumption that that's also the total pressure of our gas. Right? What mass of sodium azide was originally decomposed? Ooh. If you're feeling adventurous, try it on your own real quick. I got to erase the board, do some calculations. I might even draw a picture of this, but I'll draw a picture real quick, and then we'll do calculations on the third board. But see if you can do it on your own. Give it a shot. I tried my best. Well, not my best, but the best we can do are at home. So there's probably a few pieces missing here. We'll do something a little more advanced in our laboratory. Let's say we got a test tube with some sodium azide, an unknown mass, right? We don't know what the mass is. There's a little Bunsen burner there. And then we've got a little stopper at the top here, a 1-hole stopper. Put some glycerol in there. We got some glass tubing that we can put in there safely. Look at the video on working with glass tubing properly with great safety. And then a little rubber connector here and another piece of glass here. We probably would have, maybe in here in lab, maybe have a rubber tubing or something in there. This would probably break. You hit it down there and smash it off there. But you get the point. So we're going to generate the nitrogen gas, right? So the nitrogen gas will be generated here, travel through the tubing. No air leaks, right? Come up through here. We've got an inverted gas burette, filled it up with water, turned it upside down, put it in the vat like I showed you earlier. No air in there to start with. And then the bubbles of nitrogen go blah, 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 and start pushing water out of the burette. And let's say when this reaction's over, it settles to right there at 34.7 1 milliliters. That's the volume of gas. And inside here, we've got the nitrogen gas collected plus water vapor, right, evaporating off the surface there. Let's say we measure the temperature. You know, pretty tough to get the temperature of the gas directly. So we measure the temperature of the water. Do I have the temperature on here? What was our temperature? Fumble! I totally lost my pen. So temperature was 23.4, right? So let's say we measure the temperature of the water and assume that's the temperature of the gas. That's, you know, it's a fairly common assumption in the laboratory. And then we get your vapor pressure table. So at that particular temperature, you can get the vapor pressure of water. We'll look at that in a second here. So pretty straightforward experiment, right? So we got the total pressure, and we use a barometer to measure the atmospheric pressure of 762.7 millimeters mercury. We adjust this so that the level of the water in here equals the level of the water in the vat. So you would lower this in the experiment so the water level there equals the water level there. And then the pressure of the gas would equal the pressure of the atmosphere. So we would have to do a little adjustment and until these are equal to each other. So 762.7. Hopefully you did the math already. So I'm going to write. That took me forever to draw, man. Wasn't my strong point. I should have had my daughter come in. One of my daughters come in and do that. She's a great artist. Do the calculations for me. I'm going to erase this, and then 3 steps, right? Step 1, figure out the partial pressure of nitrogen gas using Dalton's law of partial pressures. Step 2, use the gas laws, right? You'll have P, V, T, you know R, calculate N, the moles of nitrogen gas that you collected in there. Step 3, convert that to moles of sodium azide using stoichiometry, and then convert that to grams, and you're off to the races. Let's actually calculate the mass in milligrams. Let's do that. All right. Ready for step 1? This is the easy step, right? Let's calculate the pressure, partial pressure of nitrogen. Number 1 mistake students make, they just take the total pressure and assume that's the pressure of the nitrogen. No, muy mal. We have to watch out for the contamination of the water vapor. So we know from Dalton's law of partial pressures that the total pressure measured with a barometer, so we did a little trick in the experiment to make sure our gas pressure was equal to the surrounding atmospheric pressure by equalizing the heights of the liquids. So that's going to be barometric pressure. So that was given to you, right? In lab, you would measure that yourself. Well, that's going to be the pressure, the sum of all the partial pressures of every gas. Well, we know there's nitrogen gas collected and water vapor. So we only have 2 gases. So if we add the partial pressures, that should equal the total pressure. Well, we don't know the partial pressure of nitrogen. That's what we want. That's going to be our P that we put into PV equals nRT. But the partial pressure of water is the water pressure, the vapor pressure of water at our temperature, 23.4 degrees Celsius. So get that table, the water vapor. These will be in millimeters mercury. If it wasn't, we'd have to convert it to millimeters, because this is in millimeters mercury. 23.4? So let's find 23.4 degrees Celsius. Do you see 23.4 degrees Celsius right there? So what's the vapor pressure of water? You see the 21.7? So at 23.4 degrees Celsius, it's 21.7. 21.7 millimeters of mercury, yes? So we can solve for the pressure of nitrogen. Pressure of nitrogen will be the total pressure minus the vapor pressure of water. So we're going to take the total pressure, which was the barometric pressure, and subtract 21.7. So what was the total pressure that was given? 762.7 millimeters mercury, measured from the barometer. Let's subtract the vapor pressure of water at that temperature. Good to 1 decimal, 1 decimal. So we're limited to 1 decimal place or the tenths place. Both the same units, millimeters mercury, which we could switch in torr there if we wanted to, right? So if we subtract that from that, what do you get? You get 741.0. Boom! That's the P in our PV equals nRT. Boom! So if you look at the video on gas laws and stoichiometry, from this point on, it's exactly the same as that. There's no different whatsoever. We're going to do step 2, do the gas equation to get moles of nitrogen. Step 3, figure out the mass of sodium azide. This is just an extra step because of the trick with the, well, not trick, the problem with water contamination in the real life scenario by collecting a gas by displacement of water in this case. And again, you could use any liquid as long as the gas doesn't react with the liquid. Let's do step 2, PV equals nRT, assuming ideal gas behavior. Let's see if you got what I got. All right, so first thing, I need that temperature, Kelvin, right? On my test, you don't have to show me that. You can just do it straight in your calculator. But take that 23.4 degrees Celsius, add your 273.15, limited to the tenths place, 1 decimal. I got 296.550 Kelvin, good to the tenths place, or 1 decimal place. All right, so we got our temperature. So we know PV equals nRT. We're solving for N. So divide both sides by RT. So N would be PV divided by RT. Isolate your variable. Always isolate your variable. Well, the pressure was from step 1. Remember, not the total pressure. We want the partial pressure of nitrogen, which is the 741.0. Oh, a large number of students in my class always put the total pressure there, not the partial pressure of nitrogen. We want the partial pressure of nitrogen, my friends. 741.0 millimeters mercury. All right? I divided by R here, 0.082057 liters atmospheres per mole Kelvin. I divided by the temperature, and I put that here. I could have put the temperature here as well, doesn't matter. Or gone 1 over the T. And temperature, 296.550 Kelvin. Doesn't matter where you put the temperature, just get in the denominator somewhere. I noticed that my units of pressure didn't cancel, right? So I got to convert millimeters mercury to atmospheres. So I did the 760 millimeters mercury per atmosphere. That allows me to cancel millimeters mercury in the numerator denominator, atmospheres in numerator denominator, Kelvin cancels out, right? Watching those units. Always double check the units, because if your units don't work out, you know your number's not right. All right, so I got pressure, I got RT. I need to multiply by volume, so I multiplied by the 34.71 milliliters. I noticed that the liters and milliliters don't cancel, so I got to convert 1,000 milliliters to liter. I ran out of room. I couldn't squish factor it in there. Try to do it all in one line for yourself, but take that 1 liter per 1,000 milliliters and pop it up on the end. And then milliliters on top, milliliters on bottom cancel. Liters on bottom, liters on top cancel. Leaves me with moles of nitrogen only. So I've got 4 significant digits in my partial pressure, 4 significant digits in my temperature, 5 significant digits in R. We're assuming that's exact. 4 sig figs in my volume, and that's exact. So it looks like 4 significant digits. I get 0.001390. Vertical dash line, 73 moles of nitrogen, right? Those leading zeros don't count. Captive zeros count, so there's my 4 significant digits. But always use the intermediate value. You don't want to round anything yet. I only asked you for the mass of sodium azide, right? So don't round anything until you get the mass of sodium azide in step 3, which is the next step. This is the hardest step, but it's just the perfect equation. Ideal gas equation, no big deal. So let's take that in step 3, and we did gas law. Now let's do stoichiometry. Take that, use the balanced chemical equation from the first board, convert moles of nitrogen to moles of sodium azide, moles of sodium azide, and then calculate the molar mass of NaN3 for me. And then let's convert that to milligrams. I think it said mass, it didn't say what unit, but let's go ahead and do milligrams. Next board. Did you get what I got? Here we go. So I rewrote the balanced equation. So we had 2 moles of sodium azide, solid, giving us 2 moles of liquid sodium plus 3 moles of nitrogen gas. So there's the 3:2 ratio we need to worry about, right? And let's calculate the mass. Let's do that in milligrams. If we did it in grams, it's kind of a weird one, so it gives us a nicer number. But if I just said whatever mass, you could have just left that in grams. That's perfectly fine. So let's take the moles of nitrogen we got from step 2, 0.0013907.3, good to 4 significant digits. Let's convert moles of nitrogen to moles of sodium azide using our balanced chemical equation, our stoichiometric factor, right? So we've got a 3 in front of our nitrogen and a 2 in front of the sodium azide. So we can take, woo, I'm just fumble fingers today. Let's cancel our moles of nitrogen. Boom. So that converts us to moles of sodium azide. That's the stoichiometry part of gas laws and stoichiometry problems. Let's convert that to grams. So sodium azide, we got 1 sodium and 3 nitrogens. What's nitrogen? 14.0067. What's sodium? 22.989770. So let's see what we got. Let's look at the periodic table. My philosophy is whatever it says on the table, use it. So here's sodium, 22.989770. Yep, I'm pathetic. And then nitrogen, 14.0067. All right, 14.0067. So take 14.0067 times 3, good to 4 decimal places, and then add 22.989770. That's good to 6 decimals, so 4 is less than 6. So it looks like our answer for our molar mass would be good to 4 decimal places. You're limited by decimal places. So I get 65.009870 grams of sodium azide per mole. I would normally write sodium azide up there, but I ran out of room. I like to have the NaNO3 up there, but I couldn't get it on my board. And then it asked for milligrams, so let's convert to milligrams. If it didn't, just leave it in grams, right? Why extend it when you don't have to? So I got 4 significant figures in my moles. Stoichiometric factors from balanced chemical equations are exact conversions. I got 4, 5, 6 significant figures in my molar mass. That rarely limits you. It can, but it rarely limits you. And metric conversions are exact. So I'm good to 4 significant figures. I get 60.2741 milligrams of sodium azide. Good to 4 sig figs. Put the dashed line between the 7 and the 4. The 4, one that's less than 5, right? So it's closer to 60.27 than 60.28. So it stays at 60.27 milligrams sodium azide. So we're going to do literally exactly that in lab, just we're not going to use sodium azide. We're going to use something else. And a few laboratory tricks like measuring the barometer. We got to make some corrections for, different latitudes and temperatures and whatnot. And one experiment, we're going to make the adjustment where we make the pressure of our gas equal to atmospheric pressure, measured with a barometer. In another one we're not going to do that. We're going to have an internal manometer. We got to measure the height difference between them, account for a different liquid than mercury. Oh, it gets a little crazy, but the essence of the calculations are here. Boom, meat and potatoes in this chapter, baby.